problem asks us to draw a practical mechanism. And let's take a look at the compound on the left. The OH here will be the leaving group, but by itself it's a very bad leaving group. However, the BF3 and the OH, the hydroxy group, will interact in acid and base, Lewis acid and base specifically, to convert the OH to a good leaving group. The hydroxyl here should have two pair of electrons around that, two lone pairs of electrons on that oxygen, and the BF3 here has an empty p orbital which can actually accept the pair of electron from the oxygen. And what happens is he's gonna grab, or he's gonna donate the electron to the boron to create a bond between them, the covalent bond. So if I'm to draw the resulting intermediate structure, alright, so if I assign 4 more charge, the oxygen takes a plus and the boron takes minus. And this will create a good leaving group to create a stable carbocation on this alpha carbon. Okay, when you lose the leaving group, notice that we lose the stereochemistry, so it's simply a line, and I'm gonna place our plus charge on that alpha carbon that bears the leaving group, and still keep the OAC here. But OAC, that substituent actually has a stereochemistry as well, so you need to create that, or we need to also make that thick wedge. Alright, and there is an implied hydrogen that can come over to fill that hole, our carbocation, and this is one of the carbocation rearrangement we call that a hydride shift. So I can show the arrow mechanism where he comes and fill that hole, and that's gonna create a stereochemistry because our 4 connected atoms on that carbon are different. So it looks like this, but then now we lose the stereochemistry on that substituent that bears OAC, so it simply takes this shape with a plus charge on that carbon. And then don't forget the methyl group and the hydrogen on the bridge of our bicyclic compound. Okay, as you notice that there is no methyl group on the bridge in our product. Therefore, we can also move this methyl group to the plus charge, the carbocation region, and our new carbocation is on the bridge of our compound. Okay, we're almost done, but notice that the position of the hydrogen and the carbocation is kind of resembling the elimination reaction, where the base takes the hydrogen and the bond that had the hydrogen now becomes alkene double bond on the bridge, and that simply creates the product. You see the double bond there. However, when we have the hydride shift and the methyl shift forms of carbocation rearrangement, it's good to indicate that it has a single arrow or energetically favorable form, single arrow as well, and we just completed the whole mechanism.